It's a pleasure to introduce today's speaker, Spencer Bloch from Hyde Park. It's a pleasure to have him, and Spencer will talk about, I believe, his most favorite cycle.
So thank you all for inviting me. And maybe I should, can you hear me? Can everyone hear me? Is it working okay?
I can hear you.
Okay. If anyone can't hear me, speak up. I perhaps should start out by explaining the rather facetious title. My wife told me one time about a paper she wrote for science class in grade school, and the title was Our Friend the Clam. And the teacher was not pleased, and apparently the reason was that the teacher felt that real scientists didn't make friends with the objects they studied. And that sort of worries me because as a teacher, I always worry about young mathematicians confronting what must be a very daunting, I mean, the mathematical universe has expanded exponentially since I was a young man. And it's difficult for a young person confronting such a thing, or I should imagine it would be. And you feel the need, or I would feel the need of a friend. And a good kind of friend is not a human friend, but a mathematical friend. And that's what I want to talk about, is the object that has played the role of my friend over the years. And a good mathematical friend should have two aspects. First of all, so to speak, the front door should be quite accessible. I mean, you should not have to study volumes of esoteric lore in order to at least understand the basic setup. And then second of all, the back door should lead you out into the vast mathematical wilderness so that you are well positioned to really make a contribution. And I think this example that I'm going to talk about really satisfies both those conditions. I'm not going to talk about, I've had it with me for the 40 or 50 years I've been working in this field. And so I'm not going to talk, for reasons of time, I'm not going to talk about the early aspect of the thing that I worked with along with my student Chad Schoen in the early 80s. Involving, I mean, Chad was able to use these ideas to prove some interesting examples of the Hodge conjecture, for example. I want to focus, just because there's not going to be enough time otherwise, I want to focus on recent thoughts I've had. So let me share the screen here and we'll get going. Let's see. If I click on share screen, then I click on this one, I think. Yes, this one. There. Okay, if anyone can't see my screen here, please tell me. Okay, so the object in question is an algebraic cycle. So I should start out by sort of explaining what an algebraic cycle is. I'll assume that people have some vague feeling for what I mean by when I talk about an algebraic variety, in this case y, and I want it to be smooth, so think manifold, like a manifold, and I want it to be projective, so think compact, but smooth and projective are words that make sense in algebraic geometry. And then I want to talk about the Chow group, which is denoted CHP of y, and it's a quotient, ZP of y modulo rational equivalence. And ZP of y is the free abelian group generated by codimension P closed subvarieties defined over Q. And here there's a subtlety which will be important because basically what we'll be after is the arithmetic of these cycles. And so it'd be important to keep track of the field of definition. So I give the silly example that if I consider the closed subvariety on the Riemann sphere defined by t squared minus 17u squared equals 0, then it is geometrically 2 points, these two, but the field of definition is not, the square root of 17 is not in Q, and so therefore the individual points are not defined over Q, but the sum of the two is invariant under the Galois group, so gives a point. So that's, shoot, sorry, this is going to happen. I'm sorry, there's a, this thing is, what's the story here? Okay, here we go. Okay, so then the rational equivalence is simply as follows. We take our variety y and we cross it with the projective line, which is bold-faced P1, and we consider a variety which I call capital theta inside this product, and we sort of think of this thing as being parameterized by points of P1, and the difference of any two fibers will be, by definition, in the subgroup of rationally equivalent cycles. And of course, I'm keeping under the rug all sorts of subtle questions about multiplicities and intersections and so on and so forth. But as a first approximation, this is adequate to understand the setup. Okay, so for example, if y is a curve, y is one-dimensional, and P, and 1 is also equal to a P, which will come up in a minute, then the Chow group of one codimensional cycles, so these are just points, codimension 1 cycle on a curve is a collection of points, and this contains the Chow group with a superscript 0, by which I intend the cycles of degree 0. And this thing is the classical Mordell-Weil group, which is well known in arithmetic. And we will, for purposes of this talk, always tensor with Q. We won't worry about torsion. And sometimes I may forget to write this subscript Q. Okay. So now something weird is going to happen here. I have to go, I guess. Jesus. What's going on here? Preview. Something's not behaving here. Sorry. No. There we go. Okay. Okay. So there's one other concept that we'll need to work with, and that is the Bethe cohomology. If I have a cycle, so that's a formal linear combination of these subvarieties, each subvariety carries a class in the Bethe cohomology of Y. And here, again, I'm being a little casual. Bethe cohomology is a geometric object, so really we should extend scalars and work over the complex numbers, and we do that. Right? Just it's not going to play an important role, so I just assume that we've done that. So this is a geometric object, but that's okay. We have a cycle class, and it passes through rational equivalence. And the notion I want to introduce is again the superscript 0, which will be the kernel. So these will be the cycles which are homologous to 0. And they will play an important role, as you will see. So MFAC stands for my favorite algebraic cycle. And that arises as follows. I assume that my smooth variety Y is of odd dimension. So 1, 3, 5, 7 kind of thing. And I give myself also an X, which is also of dimension 2m-1. And X, Y remember is smooth, but X is singular. And it has an isolated singular point, which is an ordinary double point. So just one double point. And that means locally near x naught, I give myself an even number of coordinates, z1 up to z2m, and x is simply defined by the vanishing of a non-degenerate quadric in those even number of variables. Okay, so that is absolutely the most plain vanilla situation you can imagine. It arises, for example, in the theory of Lefschetz pencils. If I consider a variety, say V, of bigger dimension, and I intersect it with a hyperplane, then if I move my hyperplane in a pencil, then certain elements in the pencil will give ordinary double points, but no worse singularities. So these kind of things arise quite often. Okay, so what I want to do, my y is going to be obtained by blowing up x at x naught. And that simply means replacing the ordinary double point by an exceptional quadric, which I call capital Q, which is a little bit unfortunate because it tends to get confused with the Q for rational numbers. So Q for rational numbers has a little line through it. And capital Q without a little line through it refers to this exceptional quadric. And that's a smooth variety. The quadric is a smooth variety of even dimension, one less. It's a divisor in Y. Okay. And now the key thing is that if I look at the middle dimensional Chow group, so m minus 1 in dimension 2m minus 2, so codimension m minus 1 in a variety of 2m minus 2, means these cycles have dimension m minus 1, and there are basically two of them, or that is to say the Chow group is a vector space of dimension 2, and these Li are linear spaces. And the interesting guy, which I call L minus, is the difference between these two. And of course, we have to be a little careful. I won't get too much into this, but the point is there's no canonical way. I have these two lines or these two linear spaces. There's no canonical way to orient them. And so I've chosen to write L1 minus L2, but the Galois group can switch that around. And so really this L minus is only defined in the Chow group over a quadratic extension. Well, this is not an important issue. It's a very important issue, but not for us right now. Okay, now what I can do with these cycles, or in particular with this L minus, which is pretty canonical here, up to plus or minus anyway, I can push it forward to view it as a cycle on Y. And my favorite algebraic cycle is simply the difference of those two rulings on Y. Okay, so now we should always, I mean, they teach you when you learn how to give math lectures, is to always start with a stupid example. So here's a stupid example, which has the good taste to actually be an interesting example, or at least an example that's not without interest. Suppose I take, for x and y, I take curves. Okay, so x then is simply a curve with a node. X naught is the node. And y is the curve that I get by separating out the two branches of the node. And L1 and L2 are simply the 2 points that lie over the node. And capital L is the difference in some order of the 2 points. Okay, so it's L1 minus L2, and it's an element in the Chow group of codimension 1 cycles on the curve Y of degree 0. Well, as I say, that's kind of a very easy example, not a trivial example, but a very easy example. The next example, let's go one higher. If I take m equals 2, then the dimension of y, which is 2m minus 1, is 3. And then the quadric is basically P1 cross P1. And the two lines are a point cross P1 and P1 cross a point with suitable coordinates. And so then my L minus is simply the difference of L1 and L2, and then I push it forward onto Y, which is a three-dimensional variety. And so my favorite algebraic cycle in this case is a difference of two one-dimensional cycles, one-dimensional irreducible subvarieties on a three-dimensional variety Y. Okay. Now, I want to assume a little bit more because I'm going to want to arrange that this cycle be in the, remember we defined the cycles homologous to zero with the superscript zero. I'm going to want that this difference of two rulings is homologous to zero. Now, that's not an obvious condition. In fact, it's not true in general, but it is true, and this is kind of what got me thinking about this. In fact, I should maybe say a few words. I realized, I don't know, a couple of months ago, that in this case, when X arises as a singular fiber of a Lefschetz pencil, so for that I mean we have some family, which I write script X over P1, and the fiber over zero is script X sub zero, which is my X, which is my variety, odd-dimensional variety with a single isolated double point. In that case, and if this family is a Lefschetz pencil, and I won't get into details about what that implies, but in particular, what I need is the Picard-Lefschetz theory of monodromy around, when I wind around the singular fiber, then it will be the case. I don't understand what this thing is doing. It's there, okay. Then it will be the case that this cycle, my favorite algebraic cycle, is in fact homologous to zero. And I say we will see this, and I neglected to put in a page with the argument, but I would love to show you the argument. So I've added an extra page, and if we have time, I'll go through the argument. It's a kind of argument which I should say was first due to Matt Kerr and collaborator Lazar, I believe. But it's kind of surprising that this condition implies that in fact this cycle is homologous to zero. But if I have time, I'll explain that. Okay, so now let's see. It wants me to go like that, maybe. Okay, so now I said we want to do arithmetic with these things, and maybe I should say a word why we want to do arithmetic. And basically, we want to do arithmetic because we can't do geometry. It's a sort of historical fact that the algebraic cycles, the theory of algebraic cycles, was first developed for divisors. So that is when the superscript is one, the codimension is one. And there is, for divisors, a very beautiful geometric theory. And everybody assumed that, of course, in the fullness of time, similar theories would be available for higher codimensional cycles. Well, it's not so. And the basic reason that it's not so is that cycles in higher codimensions are not really geometric objects. That is to say, they are very sensitive to the field of definition. And in particular, I took my variety to be a variety over a number field. But if I took my variety to be a variety over the complex numbers, then the whole structure of this group of cycles would change completely in bizarre ways that we don't fully understand. So that being said, we're limited in what we can say geometrically about this theory, but that's okay, because really the most interesting thing about this theory is the arithmetic. So let's talk a little bit about arithmetic, and the key objects that we need to have definitions for are the Hasse Weil L-functions. Okay, so we pick for our variety y, we pick a k, a degree k, and we study the kth étale cohomology group of y now over the algebraic closure of Q, and with coefficients, the L-adic numbers for some L. The point of all that is that the Galois group of Q bar over Q will act on this vector space. This is a vector space of over QL, but that's okay. It will act on this vector space. And for almost all rational primes, the inertia group, which I call IP inside the Galois group, the local Galois group, will act trivially. And that means that the geometric frobenius, which is essentially the quotient, will act, at least up to conjugation, on this vector space. So we have a situation where we have a collection for each rational prime, or for almost all rational primes, of these frobenius elements, and the Hasse Weil L function is obtained by simply taking the product of the reciprocal of the determinant of 1 minus fp p to the minus s acting on the kth cohomology group. And it's written L, H, K, S. So S is a complex parameter, and this will converge in a half plane because we know the eigenvalues of Frobenius, we know that. And so this is a reasonable object, at least in a half plane. Examples, if I take the stupidest example, I just take my y just to be a point, then I get the classic Riemann zeta function, which is the product 1 over 1 minus p to the minus s. And a slightly more interesting example, in fact, a much more interesting example, is to take an elliptic curve, and then I get a product where the denominator is 1 minus AP. AP is the trace of Frobenius, p to the minus s plus p to the 1 minus 2s, times bad factors for primes p, where my elliptic curve has bad reduction. So anyway, the takeaway is that this object is an extremely interesting arithmetic invariant, one for each cohomological degree. And the link, or the putative link, the link that we hope to see, was conjectured by Birch and Swinnerton-Dyer, and then the conjectures were strengthened and made more precise by Beilinson, that the order of 0 of, if we take Chow I, so codimension I cycles, and we take those that are homologous to 0, then the rank of this Chow group is supposed to be the order of vanishing of this L function at the point s equals I. And we will be most interested in a situation where the dimension of y is also 2i minus 1. So this is, so to speak, the middle dimensional cohomology of y. Okay. Now, that's a miracle. I mean, I don't think anyone has any real insight into why this is. We have a number of examples, most particularly when I is 1 for the case of curves. The notion of Euler systems due to Kolyvagin and then Kato has been very powerful in proving things about the Birch and Swinnerton-Dyer conjecture in the case I equals 1. But in that higher dimensional case, really very little is known. Okay, but the first conjecture is that this rank should be that. And then the conjecture is made more precise by the introduction of something called the height pairing. Now, the height pairing is classical, again, in the case when I is 1, but it was generalized by Beilinson and also independently by myself to higher codimensional cycles. And the point is that not only can we conjecture what the order of 0 is, but we can actually conjecture what the first non-vanishing coefficient of the Taylor series expansion at s equals I. And this first non-vanishing Taylor series expansion should be essentially determined by the determinant of this height pairing. But there's also, you have to be careful, there's also a transcendental factor, a period factor, which is fairly straightforward. But essentially, there is a pairing, and the determinant of this height pairing tells you the first non-vanishing coefficient. Okay, so that's quite a mouthful, especially since we really, outside the case of curves, we really have very few examples. And so one of the things that I would love to see my favorite algebraic cycle do is give us some examples of this, this phenomenon. To do that, so here I'm restricting now to the case where the dimension is 2m minus 1, and so this is the middle dimensional cohomology, and that has as effect that the height pairing becomes a bilinear form, and it's symmetric. Okay, so now let's see if I can push the right button here. No, that one. Okay. So what I want to outline for you here is the construction. It's a little bit complicated. I'm not going to be able to go through the whole thing, but let me focus on one aspect of the thing. And I'm going to use Beilinson's construction for reasons that will become clear, because the hoped for generalization works better with Beilinson's point of view. And Beilinson's point of view mirrors the classical point of view for points on a curve in the sense that this height pairing is realized as a sum over all places of your number field. So all primes, our number field is Q, so all primes, rational primes, together with the infinite prime, the Archimedean prime. Okay, so for each prime, we want to give a pairing, and we want then to take the height pairing to be the sum over all primes of this construction. So I'm going to focus, again, for reasons of time, on the Archimedean construction, which is, in some sense, the most important aspect of the thing. So let's let A and B represent classes in the Chow group of codimension, that's an M, codimension M, which are homologous to 0. And let's assume, and it's this assumption that we come to hate and curse, but we are forced to assume it, that the supports, so when I write straight line A and straight line B, I mean the support, so the union of the components of A and B. Remember, A and B come with multiplicities of each component. So I just ignore those and just take the union here. And so these are sets, and it makes sense to assume that they don't meet each other. Okay. And so A, as a cycle, it involves these multiplicities, and similarly B. Okay, now I'm going to do a complicated blah, 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 blah business. But after, well, maybe I'd say a few words. By purity, if I look at what happens when I take the cohomology of Y, and then I restrict to the cohomology of the open variety, which is Y minus this union of components of A, then I get a long exact sequence, which has a part like this. This cohomology that we're interested in injects into the cohomology of the open here. The co-kernel maps into a cohomology with support term, which is a direct sum of copies of Q, one for each component of A. And then the particular cycle that I chose, the choice of these multiplicities, AI, defines for me a map from Q. I put Q of 0 to indicate, well, that's a technical point that don't worry about. From Q into this direct sum here. And the crucial point is that when I go in here and I go over here, because I've assumed that my cycles are homologous to 0, this map is 0. And that enables you to do a little construction here, and you get a short exact sequence, which is an extension of Hodge structures, which has on the right Q of 0, and on the left the cohomology of that we're interested in. Now, suddenly the word Hodge structures, or the term Hodge structures, rears its head. I'm kind of going to have to assume that you've encountered that before. A Hodge structure involves, a pure Hodge structure involves a Hodge filtration So it's a rational vector space, and it has a Hodge filtration on the complexification. And this data should satisfy certain axioms. And this is a mixed Hodge structure. The weight, it involves a pure Hodge structure has a weight. A mixed Hodge structure has a variety of weights. So this is just Q with weight 0. And this is an extension of Hodge structures, which comes out of this thing. So we have that. And you can dualize this. So I did this with A now. So notice what's going on here. Here I wrote A with this straight line. So this is just a set. Here I wrote A as a cycle. And that means that what I've done is to take the pullback via this map here. And this map here depends on these coefficients AR. And so actually this pullback depends on the coefficient. So I write A and not absolute value A. Okay, so that's a construction. Now you can dualize that construction. I won't say too much. You just dualize it, and that gets you an extension of Hodge structures, where here we have Q of 1. So this is a Tate Hodge structure. It's the same as Q of 0, but I change the weight. Here, this fellow has weight -2. Okay, so I get an extension that goes the other way. And there's a whole not difficult, but a rather elaborate calculus involved in manipulating these Hodge structures. But so I have then these two extensions of Hodge structures, and they can be put together to form what's called a bi-extension. And the bi-extension I call script H of Y and A and B, and it's a mixed Hodge structure with 3 weights. So it has a W -2, a weight -2, a W -1, and a W 0. So it has 3 weights. And the W 0 is just Q of 0. And the W of -2 is a Q of 1. But then in between, there is an odd weight piece, which is the cohomology of our variety Y, but with an M twist. So M means I add -2M to the weight. So this has weight 2M -1 -2M. So this has weight -1. So these bi-extensions then are mixed Hodge structures with 3 weights, -2, a term Q of 1, weight -2, a term of weight -1, which is the cohomology that you're interested in, the pure, and then a cohomology weight 0. So this is a bi-extension. Okay, so now let me see if I can, oops, no, not that. I want to go one further. Okay. So how to think about a bi-extension? What are bi-extensions? What kind of things are they? Well, if you're comfortable with some classical Riemann surface theory, you know about the Poincare line bundle, which is a line bundle on which way did I? You know about the Poincare line bundle, which is a line bundle over a product of the Jacobian of a curve with itself. Okay. Now, you have to think about it a little bit, but that's exactly what the collection of bi-extension, that's exactly what a bi-extension is. A bi-extension sits over, there are 2 extensions involved. I call them star and double star. And this was double star here with the Q of 1, and this was star here with the Q of 0. And so a given bi-extension mapped down to the product of the 2, but it has a fiber. The fiber is essentially, well, depending upon whether you exponentiate or not, it's GM or it's GA. And therefore, you can imagine putting a metric. It's like a GM bundle over, these are actually, we can actually do geometry here. These are actually compact, complex tori. So this is an abelian, a compact abelian Lie group, and this is the same. compact sort of Lie group. This is a GM bundle over it. And this GM bundle comes with a metric. And so that gives us a real number. And that's called the height of the bi-extension. And unfortunately, it's a bit of a complicated calculation. It's you can think of the height as the obstruction to splitting your Hodge structure. So remember, H was a mixed Hodge structure, and you can try to split it over R. And the height is the obstruction to splitting H over R. But geometrically, it's just exactly like the Poincare bundle over the product of the Jacobian. Okay. So let's see, what am I trying to say here? Oh yes, there's one other key point here. We want to get the Chow group involved in this game. And the Chow group of cycles homologous to zero maps to these extensions of Hodge structure. So in other words, if I have a cycle which is homologous to zero, then zingo, I get a point on this complex, this compact complex torus. Or sometimes it's actually an abelian variety. In the case of a curve, this would be a point in the Jacobian. This would exactly be the point in the Jacobian associated to a cycle of degree zero. Okay, but that generalizes to higher dimensions as well. So I have then not only these two guys, but I have a point, and I have in fact a point in each one. And if I have a point in each one, I can look at the fiber, and then I can take the height. And my bi-extension will lie in the fiber, and the height will give me a number. So that is the interesting number. Okay, so now let's go on here. That's backwards. Okay. Now we have to criticize, right? To make that work, we have to assume that our two cycles, A and B, have disjoint support. So what I call straight line A and straight line B should not intersect. Otherwise, the whole thing falls apart. And in fact, to understand that, you can go back already to the case of curves. The height pairing, the Archimedean height pairing in the case of curves is rather easy to say. In the case of curves, the cycles are just a bunch of points with multiplicities. And associated to a bunch of points on a Riemann surface, you have a Green's function, which is harmonic, has logarithmic poles at the points. And so I have a Green's function associated to A. And what I can do is evaluate that Green function precisely because I assume that the supports are disjoint, I can evaluate that at the points of B. And that gives me a number. So that's a very nice way to think about this for points. Now, unfortunately, in higher dimensions, the Green's function becomes a Green's current, and it's a little harder to work with. But notice, either way you think, the one thing you do not want to have happen in your life is you do not want B to collapse onto A, because the Green's object, whether it's a function or a current, will have poles on the corresponding cycle. And so if B collapses onto A, I cannot integrate my Green's form over B because it's got poles. Okay, so what's the idea? We imagine, because we're interested in a function on the Chow group, and because in the Chow group we can move things, we have rational equivalence, we can slide along a rational equivalence. Very typically, and this is the point I want to stress ultimately, is very typically what we want to avoid, what we want to calculate is the height of A, sort of the height squared. In other words, we'd like to take A comma A, but we can't do that. So what do? We move A in the Chow group, and that gives us a B, which doesn't meet A, so we can then define what I've been talking about, which I now write with a subscript infinity. It's the Archimedean height pairing. And then we add some non-Archimedean terms corresponding to the non-Archimedean primes. And these are basically intersection numbers. I don't have time to say much more about them, but the idea of these is that they correct. We wanted A comma A, we moved A to B, we calculated this, but that's wrong. So to move back, we have to do a correction, and the correction are these Archimedean guys here. So that's the classical Néron-Tate construction for points, and Sasha Beilinson generalized it to higher codimension varieties. But as I say, there's a criticism. There's no canonical way to move the cycle. And what that means in practice is that the answer you're going to get is going to be weird. It's not going to have any arithmetic properties at all, except that we know that when we modify it by, or we conjecture, when we modify it by these terms, then it will have a nice property. Okay, so now what I'd like to do, the point of this lecture, and let me stress that this is very much work in progress, and I can't even formulate a conjecture, but I want to show in the remaining 15 minutes or so another way to try to do this height pairing. And the relation between this other way and the original way is purely conjectural at this point, but it looks plausible. And the nice thing about this other way is that it is completely symmetrical. We never have to move anything. Well, that's not quite true. Well, you'll see. Okay, so we'd like to understand the height pairing, and now this is my favorite algebraic cycle again. We'd like to understand his height pairing with himself. Okay, and the idea is going to be, we're going to construct another bi-extension, which has nothing to do with this bi-extension that I've been talking about, and we'll construct this one without moving anything. Well, that's not quite true. Remember, we assumed that our singular x that we blew up the double point on was the was the singular fiber in a Lefschetz pencil. So we assume that we have a degenerating family about this bad fiber. And what's more, what I need is that the monodromy, as I wind around 0 on P1, the monodromy satisfies the Picard-Lefschetz theory. There is a vanishing cycle. The variation of monodromy has rank 1, and all the Picard-Lefschetz conditions are satisfied. Okay. When that's true, I can talk about what's called the limiting mixed Hot structure, which was developed by Wilfried Schmidt and Deligne and Steenbrink and various Steve Zucker and various people some years ago. The one way to think about it is you get a vector space which I call H lim. And what is H lim? Well, one way to think about it is just take a point T naught, which is near to 0, but isn't 0. So it's somewhere in some little neighborhood of 0 on P1, and take the fiber of my family over that point. And to keep the weights what I want, I twist by Q of M, and so this resulting object has weight minus 1. But I'm not going to, I'm going to ignore that. Okay, I'm not going to look, I'm going to view this thing as a vector space with an action of monodromy, because I'm going to imagine winding around the origin, but no Hot structure. So T will be the monodromy that I get by winding around. And Picard-Lefschetz theory tells me that in this case, T is a very simple matrix. It's the identity plus n, where n squared is 0, and n has rank 1, the image of, and n is a nilpotent matrix of rank 1. The variation minus rank 1. And in that case, Schmidt and company developed a notion of the mixed Hodge structure, which depends on a choice of parameter at the origin. So here again, I promised you a rose garden, but I'm not going to deliver. I said I'm going to give another definition of mixed Hodge structure, or another definition rather of height pairing, which is not going to depend on a choice, right? Like this one depend on a moving A. Well, this one, nothing moves, but we're still going to have to make a choice, and we're going to have to choose a parameter at the origin. A parameter means really just an element in M mod M squared. So it's not really, it's well defined up to non-zero scalar, so up to Q cross. Okay, so I suppose I've chosen such a thing. Then Schmidt defines for you a mixed Hodge structure on this H lim. And the crucial point in this particular case that we're talking about is that this H lim becomes a bi-extension. And the weight -1 part and the quotient part correspond to these extensions of Hodge structure, which I call double star and star. Okay. So let's see, what do I say to clarify that? I hope I say something to clarify that. It's kind of obscure. Let me see if I can. Yeah. Well, so this H lim carries this nilpotent endomorphism, which is a map of Hodge structures. It's not an endomorphism. It's a map of Hodge structures with a twist of -1. So you give H lim this Schmidt Hodge structure, and then N maps it to itself, but with a twist of -1. So the way it works out is that I said that this H lim was a bi-extension. I said this H lim was a bi-extension, and that means it had these 3 weights. So it had a Q of 0, it had a Q of 1, and it had this middle term, which is the middle dimensional cohomology, with the twisted to have weight -1. So this has weight 0, this has weight -2, and this has weight -1. And so this H lim with the Schmidt Hodge structure becomes a bi-extension with those 3 pieces. And what's more, the 2 extensions that you get, the star and double star of a couple of pages ago, are now the same thing. Well, the one is the dual of the other, and we've not made any choices at all, right? So the question arises, how do we relate this bi-extension, and most particularly the height of this bi-extension, to the height of the other bi-extension, which is the Archimedean component of Sasha Beilinson's height construction. And this looks rather implausible, actually, because if you think about it, what have we done here? We've taken a limit. We've chosen a Lefschetz pencil converging to the particular geometry we're interested in, the particular singular X and its blow-up Y. But the cycle, my favorite algebraic cycle, depends only on that closed fiber, only on the X and the Y. It doesn't depend on my choice of Lefschetz pencil converging to that point. So at first when I saw this, I said, well, these 2 things are going to be completely different. But in fact, and this I can't show you, it's a little complicated, but when you use Steenbrink's theory to calculate so this is a Hodge structure, so what is its Hodge structure? I mean, what is the Hodge filtration? You find that in fact, the Hodge filtration on this object doesn't depend on the choice of Lefschetz pencil. So as long as my Lefschetz pencil contains my particular singular X, I'm going to get the same Hodge filtration on my H. Now, I'm not going to get the same rational structure because the rational structure is going to depend upon the choice of parameter, as I told you. And that's okay, though, because I don't expect to get something canonical. What I expect is to get something whose dependence reflects the dependence of Sasse-Beilinson's construction on how I move A to a cycle, rationally equivalent cycle B. And that actually looks plausible as well, because one thing, I can't do the calculation yet, but one thing that looks good is I can show that when I change the choice of parameter t, it changes the height by typically something like the log of a rational prime. And that's exactly the shape of what you expect. Yeah. So let's go one step further here. One further comment, and then I want to add a slide with the assertion that I made that the cycle was homologous to zero. So I want to say a word about the case of dimension 1. I still have 5 minutes. And remember, I said that friendly objects should have easy accessibility. And so the easy problem that I propose is what happens for curves. Well, so remember the situation. We have a nodal. Let's suppose that my y, my smooth curve, is an elliptic curve. So it has genus 1. So this then becomes a curve with geometric genus 1, but arithmetic genus 2, because I have this crossing point here. Okay. Then what you have to do, and I'm in the process of doing it, but I can't say I've done it yet, is you have to work out, you have to write down a degeneration of, now you actually need to consider genus 2 curves. Your Lefschetz pencil is going to be a family of genus 2 curves degenerating to this singular curve here. And then you have to work out the corresponding bi-extension and its height. This is all doable, but it's not easy. But this should show whether my fantasy that this gives another way to think about the height pairing has any basis or not, because we should be able to see from the case of curves. Now, notice one other thing before I let go on the case of curves is that we can the case of curves is so simple, we can kind of reverse engineer things. You might say, for example, gee, how do I know that this cycle, your L minus, it could always be trivial, right? How do I know it's not just always zero? Well, one answer, I mean, there are many ways you can show it's not always zero, but one answer is just say, okay, let's look at the case of curves. Let's start out with an elliptic curve y. Let's choose, say, I'll take the plus here to be the origin and the minus to be some other point. Okay, and then I'll glue at that point, and that will get me my x. And then I can lift, I mean, these are curves, so deformation is unobstructed, and I can lift and build myself a family degenerating to x. And in that way, I can show that depending on how, if I take x to be 0 and y to be, and the minus here to be some point of infinite order, then I really have built a situation where my cycle, which remember is just the difference of the two, is actually a point of infinite order. Or conversely, I could take a point of finite order, and then I could build an example where my cycle has finite order. Yeah. So, okay, in the remaining 4 minutes, let me go back to the thing that I omitted here. Let's make this go away. And let me stop share and then start share again. Start share again. And then I want this one here. Okay, share. Okay. So now you should see something that says omitted from talk. How do we see that my favorite algebraic cycle here, there should be L minus here, there's a minus, is homologous to 0. So remember that we were in a Lefschetz pencil, and Y was obtained by blowing up X naught on X, and the exceptional divisor is this non-degenerate quadric, which I call capital Q. Okay, so now we combine several things. First of all, if I look at the cohomology, the relative cohomology of X relative to X naught, then that is the same as the cohomology of X, because even when M is 1, this is H1, but there's only 1 point, so relative cohomology is just the same. Okay. So on the other hand, this is by excision, this is isomorphic to the relative cohomology of Y relative to Q. Okay, so that's the first point. The second point is that I have, for this relative cohomology, I have an exact sequence. So I can look at the cohomology of Y in degree 2m minus 2, restricts to the cohomology of Q in degree 2m minus 2. This is the piece which is the two rulings of my quadric. So this is just a vector space of dimension 2. And then I go up 1 degree to the odd dimensional cohomology of Y. This is the cohomology group that interests me. And then I go, sorry, this is the relative cohomology group, and this is the cohomology group of Y. Okay. Now, if this cycle here is not 0, sorry, I should say in cohomology, I should have written, if this class is not 0 in cohomology, then this map is surjective. The target is 2-dimensional, and we have L minus here, but we also have L plus. But it's easy to see that if L minus has a non-zero image, then in fact the image is 2-dimensional, and L plus and L minus have distinct classes, and so this is a surjective map. So this map becomes surjective, and that implies that in fact this relative cohomology group is actually isomorphic to the cohomology of Y. Okay, but if this relative cohomology is isomorphic to the cohomology of Y, then Y is a smooth projective variety, so this is then a pure Hodge structure. But if this is a pure Hodge structure, then excision is going to tell me that this is a pure Hodge structure. So we have, and if this is a pure Hodge structure, then this is a pure Hodge structure. So we have that the cohomology of X is a pure Hodge structure. But finally, the Clemens-Schmidt exact sequence, when Schmidt developed his theory of limiting mixed Hodge structures, came with a sort of exact sequence of Hodge structures, which would take the cohomology we're interested in. I've put a twist of M here to make this a weight -1. And this would map to this limiting mixed Hodge structure, which remember has weights -2, -1, and 0. And then there would be N, this would be an exact sequence. That's part of their Clemens-Schmidt theory. There would be an exact sequence, and the image of n is one-dimensional. So if the image of n is one-dimensional, then this kernel here has to have two distinct weights. So if this kernel has two distinct weights and this is pure, we have a problem. So it's not possible if this is pure, and the contradiction came because we assumed that this class was non-zero. Okay, I'm out of time, so I'll stop.